Hello, welcome to the new you. So today we'll be opening a new section or chapter in this course. And what you see from here to the rest of the class is very important topic on a new notation that we will be using. That is what is called the state space modeling. Let's zoom out for 1 second and see where we are. So we have started from some dynamical system, a mechanical, or this could be anything, either physical or non-physical system, such as population growth or economy or anything like that. So at the beginning of the course, we started just looking at the equations of motion, if it's a mechanical system, and we analyzed or looked at the response of that system. We took the natural and forced responses and see how it behaved. So that was one way we analyzed the system, just looking at the raw equations. The second step we took was introducing a new notation called transfer functions. It was a way to describe the same dynamical system through another kind of notation. It wasn't anything special. The only thing that made it special was that we categorized or created this compact way of describing the input-output relationship of a system. And through that power of this notation, we could analyze things that was not readily obvious using just looking at the equations of motion and the response. For instance, we looked at the stability of the system, we looked at the frequency response of the system, which all became possible using this notation. One thing to emphasize and remember here is that transfer function is only valid, and we can define a transfer function for a linear time invariant system. So if our system is anything other than linear or it changes with time, transfer function doesn't work. Also remember that transfer function is an input-output relationship, meaning that for any input and any output, you have to define a single transfer function. So it is possible that your system may have multiple inputs and multiple outputs. And working with transfer function in that kind of multi-input, multi-output situation is a little cumbersome because you have to define individual transfer function for each combinations of inputs and outputs. That is where state space modeling comes in. Again, it's also a kind of notation. It is nothing extra to what we had before. We are still working with the same dynamical equations of these dynamical systems, but we are introducing a kind of notation that gives us a lot of power. And this is state space notation or state space modeling approach is powerful because it is not restricted to linear systems, it is not restricted to time invariant systems, it is not restricted to any number of inputs and outputs. This is, at least as far as I know, one of the most powerful and general purpose ways we can start to model and analyze a dynamical system. So let's begin by a few, and maybe before that. So this state space modeling is rather new. I think it's one of the newer methods of describing and analyzing a dynamical system. And it is very, very well suited for the kind of numerical analysis we do on computers. So I don't know which one chicken was first or the egg. But this state space modeling goes hand in hand with a lot of computational tools that we have in the space of numerical analysis. So, okay. So what is the state space modeling? To do that, let's do a few definitions first. Some definitions. So what is a state? state essentially is the minimal set of information you need to have in order to describe the current state, for the lack of a better word, describe the current state of the system. And if you know the inputs to the system, you will be able to fully describe the outputs or the behavior of the system for the entire time. So this state is the minimal set of information that fully describes systems current. I don't have a better word, so I'm going to put state in a double quote, state, to distinguish this state and that state. Current state, and plus knowing inputs, describe minimum to fully. This fully is important. Describe behavior. That's British behavior for all future time. So if we know the current, this minimal set, and we know the input, we should be able to describe the system now and for the entire time. That is what we call a state. The next one is a state variable. This one is easier to define. Any one of those bits or pieces of information. Any let me put it as one word. Any one of variables that make up the state. So there is one thing here that usually when we say state, we are lazy, we don't say state variable, and we call a state, or two of these states are unstable. We mean this and kind of substitute the state variable for the general state definitions. So be careful, but from the context it's going to be fairly obvious whether we are talking about the single one of them or the collection of them, the whole set. What is next? And one thing, maybe a side note here, is that these state variables could be anything, either physical or non-physical. It could be the amount of money, it could be the, I don't know, a combination of a few physical parameters or a single physical parameter like position. So this, there is no restriction what this variable is in terms of its nature, as long as the collection of all these states can describe the system, we are good. Next one is a state vector. State vector is now the mathematical formalization of a state. So it's so if you have n states, let me see what I have here. Yes, this is an n dimensional vector containing state variables. So it's just a vector of numbers, and each of those x1, x2, to xn, each of these are one of these state variables, and this is our state vector. Usually we denote it by x, but not always. Next step, state space. Well, maybe I don't need this. State space. Again, this is a mathematical concept. Is the vector space. There are specific conditions what is a vector space, but we don't get into that. A vector space that contains vector space containing these state vector. So for instance, if you have an n-dimensional x, your state space is going to be Rn. And again, one thing to maybe note, we are usually dealing with real variables, real state variables. So my state space is an n-dimensional Rn in real numbers. So for instance, if I have n equals 3, my state space is a vector containing these x, maybe x1, x1, x2, x3. This is my state space. And my state vector in this case is x1, x2, x3. And the last but not least, state equations. Equations. So these are what describes the behavior of the system, the dynamical behavior of the system. And it is the relationship between the derivatives of states and the current values of states and input. You see, I use a state as a substitute for a state variable. So I do that always. Everybody does that. So let me write it in Word. Relationship between state variable vars derivatives. Let me put time derivatives and current state variables plus inputs. So this means is that my state equations are a set of equations in an n-dimensional state space. So I have x dot 1 equals some function of x1 to xn and u1 to um, however number of inputs I have, and so on. x2 equals some f2 of x1 to xn, u1 to um, and all the way, it's a dot, x dot n equals some fn, x1, xn, u1, um. So the collection of all these equations relating the derivative of one state to the rest of the states and inputs It's called the state equations. And one important thing to note here, it is always first derivative. So it's not x double dot or x triple dot or any other thing we have so far worked with. This is always the first time derivative. Maybe I can. Between a state vars, first of all, it needs an apostrophe here. First time derivative. And the current states and inputs. Okay, so I'm running out of space, state space. Let me clean up the board and pick up one example, and then we can continue. Here is our famous low-yaw example, a cart, a mass spring damper system. And I'm not going to redo the free body diagram. This is the equation of motion. So now let's try to rewrite this system in a state space form. Note that we have here y double dot. And for a state space equation, we said we want always the first time derivative in our equations. Something we can do is a little change in variables. So let me call x or x1 to be my y. And let's call x2 to be my velocity, v. Now if I want to write the state equations, so let's define this, and x dot 1 equals y dot equals this v, velocity of the car, which is x2. So x dot 1 equals x2. What about the second state equation? X dot 2 equals v dot, which equals v is velocity, so v dot is acceleration, or y double dot, which I have the equation here. That is y double dot. I'm going to divide this by 1m, so minus k over m y minus b over m y dot plus 1 over m u, and just reusing the notations of x1 and x2. So y is x1 minus k over m x1 minus b over m. Y dot is velocity, which is x2, plus 1 over m u, which is my input. So maybe if I want to make this a little nicer, x dot 1 is x2, x dot 2 is minus k over m x1 minus b over m x2 plus u over m. So these are the state equation or state space equations for this cart and pendulum system. What did I say? Cart and pendulum? No, a mass spring damper system. So again, similar to the case we had with the transfer function, we are not really doing anything special with our system equations. We are just form it through a kind of a new notation, and the notation has the power, as we will see soon. It can open new doors for analysis of the system. So now let's try to generalize a little. The next page. So in this course, we are still completely looking at linear systems. And as you can guess, the state equations will also be always linear. And they will look something like this. X dot 1 equals, let me check my notation, a11 x1 plus a12 x2 plus dot 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 2 plus a1n xn plus b11 u1 plus b12 u2 plus dot dot b1m um, and same x2 equals a12 x1 plus a22 a2 a21 x2 plus a2m xn plus b21 u plus b1 u2 b2m or a2 x n equals a1 plus a2 x2 a n xn plus b n1 u1 b n2 u2 b n n. So this is the most general form of a linear state space equation that we have within each equation representation of all states. And remember, we are dealing with linear equations, so we will not have multiplications of x1 and x2 or x and u's. So all of them show up only in this linear form. Now, what we can do, this is quite long and I had to speed up the video because I didn't want to write all of that. So that's cumbersome to work with. And here is the true power of this state space modeling approach, that I can now very compactly write, let me put it this way, d over dt of, oh, I did that, x1, x2, to xn equals a matrix consisting of a11, a12 to a1n, all the way down. Maybe I can write another row. a21, a22 to a2n, an1, an2, ann, multiplied by same state vector x1, x2, x3, plus same thing for the inputs, b11, b12, b1m, I'm not going to write the rest, bn1, bn2, bnm, time u1, u2, um. And finally, I can do this. Let's call it the state vector x dot equals, let's call this sum matrix A. Well, this one is x. Let's call this sum matrix B. No, not this. And this is the vector u. So x dot equals a x plus bu. This is the kind of equations we will be working from here on. So it's a linear combination of all x variables, multiplication by in compact form by a matrix A. Same thing. Let me make it as capital B. Bu plus bu. These two are matrices. X and u are vectors, and I can relate the derivative of the state vector linearly to x and u vector. So one thing let me check if I'm not missing anything. The input matrix, state matrix. Okay, so this is the vector of derivatives of states. I have n states. Usually these are the kind of a standard notations. So I usually have an n by 1 state vector. My A matrix is always a square matrix n by n. And same thing for my state vector. It is n by 1. B is n by m because I need n rows because of the n equations. And I have m inputs, u1 to um. And my u vector is m rows 1 column. Maybe already you can see why we are doing it this way to have the first derivatives, because now we have this very compact form and the entire system dynamics is defined through a matrix of just variables, numbers, A and B. A very nice compact way to describe dynamics of a system. And maybe a side note here, this notation is not restricted to, it is restricted to linear systems, obviously, because we should have linear equations to be able to write it in this form, but not time invariant systems. So if these variables A's and B's change over time, we can have time varying A and B that also change with time and describe this time varying behavior over time. So those are my state equations. There is one other thing that shows up very commonly, is something called, do I have, yeah, let's try to put it here, called the output equations. So I have a system described by these state variables, x1 through xn. It is possible. So imagine this is the Cartan pen, the mass spring damper system. And what I'm going to do is to try to measure something out of this system. For instance, I don't know what I want to measure. Maybe the force in the damping, or force in the spring, or any other thing. So those are my output equations, or outputs from the outputs of the system that could be different from my states. So the standard notation is usually used y to describe the outputs. So I can have one y1 equal, again, a linear combinations of the state, same form as that. So I hope I can write it more compactly or quickly. So I could have a different number of measurements or outputs that I can get from the system up to some measurement yr, and if my measurements or outputs are again linear combinations of the state variables and inputs, I'm just going to continue writing here. Similar as the case I had with the state equations, I can write my output equations, my y, which is r by 1 equals some matrix C11, C1n, CR1, CRn times my x. Let's put this one here. x1, xn plus, this is going to be my D matrix, D11, D, what do I have 1m dr1 drm times u1 to um. And this is called the C matrix as just commonly used notation. It is R by n multiplied by my x, which is n by 1, plus this is D matrix R by m multiplied by u m by 1. And in both cases, obviously, if you work out the dimensions of the matrices, you will get the same dimensions that you're supposed to. So maybe something I should mention here. This one A is often, or not often, sometimes. I don't use this word, but this is called the state matrix. Let me write it in a different color. This is state matrix. This B is called the input matrix. Input matrix. C is called the output matrix. And D, this one, I did all of that because of that. That D is sometimes called what? Direct transmission matrix. So it's a direct feed through of the inputs and their effect showing up in the output. Okay, now I have that. And I wish I had a little bit more space, but I'll keep that for the next board. So let me clean up and I'll be back. So just to rewrite the equations here, what we have here is the compact way of writing the state equations and output equations through a series of matrix manipulations. And I have the state vector, the input vector, and output vector multiplied by the corresponding state, input, output, and direct transmission matrices to give me the equations, the state space in a state space form. So that is a very compact and general form that we can cast any linear system, linear dynamical system into that form, and later on we can analyze those. So just going back to the example that we had. So this was my mass spring damper system with the input U. It was a force. And we just calculated before I erased the board that my two states, x1 and x2, x1 being position and x2 being the velocity, I could write the equations as so. I have just added a bunch of zeros, essentially, just to make things more clear. And the way I have written it, now it is a lot easier to use it in that notation. Also, let's assume my output, the measurement that I'm taking out of the system, is the position of the mass. So it is essentially x1. The rest of them are 0. So I have written it this way, and if you do it so, it is going to be relatively easy to see how the matrices A, B, C, and D should look like. So I have 0, so it is going to be multiplied by x1 and x2. This is my A matrix. So I have 0 x1 plus 1 x2. On the other, on the bottom one, I have minus k over m times x1 plus something x2, which is minus b over m. And let's complete this. So I have 0. Well, it is going to be multiplied by just a scalar u. So I have 0u, and on the second one, 1 over mu. And from here, my A matrix is, what is it? 0, 1 minus k over m minus b over m. My B matrix is 0, 1 over m. And let's work out the output equation as well. So it is just one row multiplied by x1, x2. So I have 1 x1 and 0 x2 plus, and my D matrix is just going to be a scalar, so only a matrix containing value 0 times u. So from here, C is 1, 0, and D is just a matrix of 0. So that is that. We'll be solving more examples later on how we can write any linear systems dynamics into this form. So that would be a lot of exercises. So what else? So this form, now that I have it, let me, first of all, this state space form, either in linear equations as we have the matrices A, B, C, and D, or in its nonlinear form when this equation is a collection of nonlinear functions, is essentially the basis of the entire modern control. A lot of the new control algorithm and analysis method are based on this. So in this regard, the transfer function notation that we have used before is the older generation, I would say. It is still very powerful, and a lot of analyses and information can be obtained very easily using that notation. But the capabilities of state space notation goes beyond, partly because we are harnessing the entire power of linear algebra. The entire methodologies that are based on matrices and vectors can come aid us in creating more powerful analysis methods and design methods in controls. Also, I want to mention that this formation, this way of writing the equations, especially the fact that we are only working with the first order time derivative, is extremely suitable for not analysis or making any generalize any argument about the system, but just to solve a dynamical system numerically, and assume that I have, even in its general form, x dot in its vector form equals some f, a number of functions that are functions of x and u. And by the way, before I continue, I often drop the vector notations, this one, because from the context it would be fairly obvious whether we are dealing with a scalar or a vector. But here, for me to be a little explicit, I put them. So even if it's in its most general case, if I know current x and if I know current u, I can calculate x dot and solve that numerically. So x of next with an approximation could be my x dot times my small time step plus x of now. And you can see I can easily calculate x dot if I know x, and then calculate the next value and continue over time. So this is extremely well suited for numerical analysis. This notation is good for all sorts of numerical methods. And essentially, if you use any numerical package such as MATLAB or in Python or any other thing, you need this. You always need to work out what are the first time derivatives, and you have to stack them, and then the algorithm can take the integral either in this simple form, which is called Euler integrator, or more advanced or more accurate methods. You can increase the order of your integration accuracy. But this form persists. It is a common starting point in all of them. Okay, I'm about the end of this lecture. The only thing that maybe is useful to point out, two more things. One, kind of trying to link this state space form and the ideas we had before. So first one, let's look at the block diagram, block diagram equivalent of that notation. So I want to build something that I receive input u, something in the middle, and get output y, right? So in a transfer function notation, this entire thing was collapsed into one transfer function in the middle. But with that notation, we can do similar thing. It needs a little more things in the middle. So somewhere in between, I have to calculate x, my states. And these states come from the integral of my x dots, the derivatives. So if I have somehow magically calculated my x dot, I can take the derivative, get the x out. Now if I have x, I can multiply it by my C matrix. Now have this first bit constructed. And let me maybe clean up a little and make this bigger, and then I can branch out, feed through my input also, so I have now both cx and du, so I can add them together. So this one is added, that one is added too, that is my y. And how do we construct this? It's relatively easy. So to get x dot, I need bu, so I can do this, multiply it by b, so now I have bu. I also need ax, but I have x already, so I can take this here, multiply by an a. This is my ax that I can add to bu to finally get the x dot. So this whole thing is the transfer function that we were working with before. So it is useful to have this kind of analogy or cross-linking between the two concepts. This is one of the ways that we can think how transfer functions and state space notations of describing the same system can be related. And the last comment I have is, what are these states? That is not by any means a simple question. So here I kind of magically figured out, if I take my state number 1 to be the position and state number 2 to be the velocity, I can write the original second order system equation into this state space form. First of all, this choice, as we will see in more detail later, is not unique. You can have an infinitely possible combinations of variables, and they are all equally valid. I started with something that should have 2 parts to it, but I forgot. Yeah, it's not unique. And how we can find them is not trivial. But in mechanical system, there are kind of guidelines that usually work in mechanical system. Where we have a mass, essentially, we're dealing with accelerations. We had this before, that for every degree of freedom, we have 1 second order differential equation. And what we can do for, let me write it down, for every degree of freedom, I can take the position, or let me write it as, let's do this, x1 to be position, that's the best, position, and x2 to be velocity, both of them related to the degree of freedom that we are writing the equations for. This, kind of using the position and velocity as the 2 states, will almost always work, with some exceptions, when there is a weird condition of either you don't have inertia as your degree of freedom, so in most of those cases you don't need to work with velocity and keep the position as your only state, and there could be situations when you have the derivatives of input showing up in the state equations, then this guideline doesn't always work, and we'll see, we'll touch on it a little, that what we can do. But position and velocity are the usually chosen variables as the states for each degree of freedom. So that's all I have for now. We just introduced the concept of state space, and we'll see in the next few lectures, basically until the end of this course, how we can use the power of this notation to analyze our system and get more information out of it. So until then.